This is part 1 of 5.1, going over a couple logarithm derivatives, and I'll give you a you-try problem near the end and talk about some tips or things you can do to make these problems a little bit easier. Before we go over any definitions for derivatives, these are definitions you learned in Algebra 2 and Pre-Calc. You can pause it, copy these down. It's a good way of sort of as a refresher. What this property says is that if you're multiplying, you can add individual logarithms. This one says if you have an exponent within a logarithm, you can drop it down in front. If you're dividing two things, you have a fraction, you can subtract individual logarithms. And these two, I've noticed over the years, students get these confused or maybe don't realize that their properties, that the ln of e is equal to 1, so the ln and the e sort of cancel each other out. They're inverses. And that the natural logarithm of 0 does not exist. For some reason, this one is one that students think that ln of 0 equals 0, or don't remember that ln of 0 is undefined. I can go over with some of these with you in class individually if you have questions of where these properties came from. But alright, now going over the actual derivative of a logarithm. Derivative logarithms are kind of funky in the sense that they start off as a transcendental function and they end up with an algebraic derivative. So what that means is that logarithm of ln of x, the derivative is 1 over x. And if you have something that involves a chain rule, it's going to be ln of u, it's going to be a u prime over u. Alright. So first example, find the derivative to f of x ln of this. Now, before you jump into trying to find the derivative, we're going to use these ln properties to simplify things as much as possible. So, the first thing I notice is that this is all a square root, so I can write this as f of x equals, ln of 4x plus 1 all to the 1/2. So you can think of everything that's inside the radical is all raised to the 1/2. And then the property says, this one, that you can drop this exponent in front. So I can drop this 1/2 in front of ln. Alright, and I still have not taken a derivative yet. It's just still the initial function. This is still f of x. And then from here, I can go ahead and find my derivative. So now I can say that f prime is equal to, and now the definition of a derivative of ln, it's going to be rewriting whatever is on the inside into the denominator. So it's going to be 1/2 times, I'm just going to recopy what's on the inside, 4x plus 1, which is this part. And then the derivative, the u prime, is the derivative of this inside. The derivative of 4x plus 1 is just going to be a 4. Alright? And then I can simplify from there. I have this 1/2 and this 4. I can reduce this. This just becomes 2. So this simplifies as just 2 over 4x plus 1. And that's my derivative. Alright. Going over the next example. Now I have a g of x is equal to this, and I want to evaluate the derivative at 3. So again, using these logarithm properties to simplify things, if I'm dividing something inside a logarithm, I can subtract their individual logarithms. So I have g of x as ln of x minus ln of x squared plus 1. Alright, so this is not taking a derivative, this is just using this property to simplify things before I take a derivative. So now g prime is going to be the derivative of ln is just 1 over x, so this is going to be 1 over x minus, because this involves a chain rule, I'm going to use this one over here, which is u prime over u. So the u prime, the derivative of x squared plus 1 is 2x. over x squared plus 1. Alright. Now I wanted to evaluate my derivative g prime of 3. Since I'm only looking for a numerical value, I'm just going to plug this in. I'm just going to go g prime of 3 is equal to 1/3 minus 2 times 3 all over 3 squared plus 1, which simplifies to 1/3 minus 6 over 10. Finding a common denominator, or I can reduce this 6 over 10, reduce this to 1/3 minus 3 over 5, common denominator being 15. This becomes 5, this becomes 9, and my answer is going to be negative 4 over 15. So g prime of 3 is equal to negative 4 over 15. So the main idea is that if you have a logarithm that has multiple terms in it, you want to use these properties to simplify as much as possible, and then just take individual derivatives. So the derivative of this term and the derivative of this term makes it a whole lot easier. Alright, there is one you-try problem. So I'll go ahead and put it up for this part. So try finding the derivative of this. My advice to you would be to simplify as much as possible. So use these logarithm properties to give each one of these its individual logarithm and then take the derivative. So you get this point, you can pause it, try it yourself. Alright, so you should have tried it now. I'm going to flip it on over and show the answer. So the first thing I do is I split this up because it's a product. I can add individual logarithms. This is the square root, so it's all raised to the 1/2. I dropped the 1/2 in front. Notice I'm only simplifying. I haven't taken the derivative yet. Then I go ahead and take the derivative. So the derivative of ln of 2x is 2 over 2x. This is going to be 2x over x squared plus 1. And what I did from here, I didn't write it down, but I just assume you can see that I reduced these 2's, and I reduced these 2's, and I got this as my answer. Now, this could be your answer. However, if you find common denominators, you can find x and x squared plus 1 as your common denominator, and then this will be your equivalent answer. So this simplifies to this, which brings up the last point I want to make for this video, and that's going to be how much do you need to simplify. Now, you don't need to copy this down. I can just kind of talk through it, and it's going to be how much you simplify is basically as much as you need to. If you need to match a multiple choice answer, maybe if you're doing this problem and this answer isn't listed, then you might have to simplify in order to get to here. If you want to maybe match an answer in the back of the book. If future steps are simpler because you simplify, so I can't really think of a reason for this example, but it could be that maybe a next step in a similar problem would be simpler if you're able to simplify or reduce this somehow. So the last one is if you can handle the algebra. Oftentimes students invent or create their own algebra rules when they're trying to simplify, so if you don't need to, it's best to just leave it the way it is. If, let's say this is free response, and you got to here, since this is equivalent to that, you would earn the same points as for this answer as you would this answer. So if you don't really know what you're doing, if you can't really find common denominators, if it's going to get messy, then I would just say leave it like that. However, if it's multiple choice, then your algebra skills probably will be tested, so you probably do need to get to here. So as far as how much you simplify, it just depends on, you know, what the situation is and what you need to do with the problem, with your answer. Alright, so that's it for this video.